Hi, I'm Brian Goslin, an applications engineer for Texas Instruments' integrated signal chain product line. Today I'm here to talk to you about analog temp sensors and how they compare to NTC thermistors. NTC thermistors are commonly used in the industry due to their low cost and the wide variety of package options available. However, today I'm here to talk to you about why you might want to design in an analog temp sensor instead of an NTC thermistor. Let's first start by comparing the output voltage versus temperature curves for both an analog temp sensor and an NTC thermistor. This is important when interfacing with an ADC because you want to make sure that the ADC can detect a change in temperature. Let me show you what I mean. NTC thermistors require the use of a resistive network in order to help linearize the output, as the resistance versus temperature characteristic is exponential. The NTC thermistor network that I am showing here on the right is a simple voltage divider circuit with the bias resistor on the top and the NTC thermistor on the bottom. Note that the output voltage of this circuit is the voltage across the NTC thermistor. The axes on this graph is output voltage in volts on the y-axis and temperature in degrees Celsius on the x-axis. The yellow, blue, and green curves are all output voltage versus temperature curves for an NTC thermistor rated at 100 kiloohms at 25 degrees Celsius. The difference between these curves is the bias resistor value. Yellow is 100 kiloohm, blue is 30 kiloohm, and green is 10 kiloohm. You can see that if you adjust the bias resistor value, you can essentially adjust the linear portion of the curve. Notice that the curves start to saturate at low and high temperatures. This is one problem that engineers face when using thermistors. The saturation at low and high temperatures may cause temperature errors due to the resolution of an interfaced ADC not being high enough to detect a change in output voltage per degree Celsius. Thus, engineers may have to use a higher resolution ADC to account for this error. This is a problem that is not seen with analog temp sensors, as they have a virtually linear output. For example, you can see in the graph that Texas Instruments' LMT87 analog temp sensor provides a virtually linear output across the device's entire operating range of -50 to 150 degrees Celsius. When interfaced with an ADC, analog temp sensors tend to be more accurate across the device's entire operating temperature range. Another thing to note is that analog temp sensors do not require the additional components, such as the resistive network that is required by the NTC thermistor. This is important because those additional components adds to the cost and the footprint of the overall temperature sensing solution. Let's now take a look at a supply current comparison of analog temp sensors and NTC thermistors. Supply current is important because it directly relates to the amount of power that is dissipated by the overall temperature sensing solution. Let's take a look. The axes on this graph is supply current in microamps on the y-axis and temperature in degrees Celsius on the x-axis. You can see that the LMT87 has a typical value of 5.4 microamps and a max value of 9 microamps, while the NTC thermistor network supply currents are much higher and vary greatly with temperature. As a result, NTC thermistors tend to dissipate much more power than analog temp sensors. If using an NTC thermistor, engineers need to take into consideration the self-heating effect, as this will cause additional errors. Note that if you increase the resistance of the bias resistor, the supply current for the NTC thermistor network will decrease. However, remember that the bias resistor is also chosen such that the output voltage versus temperature curve is linear for the desired temperature range. As you can see, this is a trade-off that must be taken into consideration when engineers are using NTC thermistors. This is another issue that can be ignored by using an analog temp sensor, as analog temp sensors have both a fairly constant low supply current and a virtually linear output voltage across the entire operating temperature range. So how do we come up with this data? I designed a test board here that compares NTC thermistor networks with TI's LMT87 analog temp sensor. We were able to record the data by using the oil bath setup behind me. One last thing that I want to mention is in regards to output impedance. NTC thermistors tend to have a much larger output impedance than analog temp sensors. When interfacing with an ADC, it is important to make sure that the ADC can handle the output impedance of the NTC thermistor. If the output impedance is too large, a buffer may be required. This is an advantage of analog temp sensors, as their output impedance is small and does not require a buffer. For more information on LMT87 and other analog temp sensors, as well as technical conversation, please visit the following links.